Sometimes in the real world, we have a situation that cannot be easily modeled using a single formula. For example, suppose a store is selling flour in bulk for $3 a pound, but they have a bulk discount. If a customer buys at least 5 pounds, the bulk discount kicks in, and the price drops to $2.50 per pound. We want to write a function describing the price of flour. So our variable is the number of pounds of flour we're buying. The output of the function is going to represent how much we're going to pay. And we have a problem, right? Because the price is $3 a pound, as long as we're buying less than 5 pounds. If we buy 5 pounds or more, then the price goes to $2.50 a pound. Now, this sort of bulk discount always annoys me because I feel very strongly that 4.5 pounds of something should always cost less than 5 pounds. But let's not get distracted by that issue. Instead, let's think about how we can describe this. Certainly none of the functions that we know gives us a single formula that we can use to write this down. The best we can do is what's called a piecewise function. The way we would express this is to say, well, p of x can be one of two things. It can be 3x if x is less than 5, or it can be 2.5x if x is greater than or equal to 5. So this is just a notational way of expressing this situation. So if we buy 2 pounds, well, the price of 2 pounds, for 2, we'll use this rule. So we'll have 3 times 2 is 6. If we buy 2 pounds, that costs us $6. On the other hand, if we buy 8 pounds, well, the price of 8 pounds, if we buy 8 pounds, we're buying at least 5, so we use this rule. The price of 8 pounds is 2.5 times 8 is 20. If we buy 8 pounds, we pay $20. So this is what's called a piecewise function. It's a function that's defined not on the whole number line, but just on pieces of the number line, hence the name piecewise. So we'll see a function like this, given a notation that looks like that, or notation that looks like this next example. What we see here is first the name of our function, and then various expressions that might describe our function for various values of x. When we go to evaluate a function like this, our first step is to figure out which of the given ranges our input is in. So if we want to take f of -4 here, we see that -4 is in this range, right? It's true that -4 is between -5 and -3. So that means that f of -4 is 3 times -4. We now plug the -4 in for x, which is -12. If we want to take f of 2, well, 2 is not in the first range. It's not between -5 and -3. 2 is between -3 and 3. So 2 is in the range where we use the second formula. F of 2 is -1/2 times 2 squared which is -2. 3.5, well, it's not between -5 and -3. It's not between -3 and 3. 3.5 is between 3 and 4. So that means 3.5 is in this range, which means f of 3.5 uses this expression. That expression expresses a constant function. It says for any number between 3 and 4, the value of the function is just 3. So f of 3.5 is just 3. If we have 5, well, 5 is greater than 4, which means that we use this formula. F of 5 is just telling us our input back. So f of 5 is 5. Now there's a complication that comes up here, though, when we try to take f of -3. And that is, -3 doesn't fit in anywhere. -5 is less than -3 is less than -3, that's false. -3 is less than -3 is less than 3, that's false. There aren't any of these conditions that -3 meets. So f of -3, -3 is just not in the domain of our function. F of -3 is undefined. That's what we say when a number is not in our domain. So these piecewise functions, when we're given our input, we first look at which category that input falls into, and then we use the formula associated with that category. If our input doesn't fall into any of our categories, then it's not in the domain of the function, and the function is undefined.